Okay. Before we get started with our notes for today, just a brief announcement. This announcement is going to go out tomorrow. It's more so directed towards the remote students. Tomorrow is the end of the quarter, and we are having a homework check. This does not breathe very well. On section 4 in class tomorrow. It is due Sunday evening. So if you have any problems, if you forget to submit it, this goes for anybody. If you forget to submit it in here, which seems to be a common theme with not necessarily in this class, but in other classes. Okay, it's the due date is going to be Sunday by 11:59 p.m., not Monday. So when you are doing those, make sure you get them complete because it will be your last grade for third quarter. So I just had to mention that today. After our notes today, we are going to do a couple of additional problems as a class. I took the homework away that I was going to do just so we could do a couple of sample problems in class. Okay? Yes. I don't know about a pen or pencil, but I have a pencil. Might need to sharpen it a little bit. There's a sharpener here. So while that pencil is getting sharpened, let's just recap what we discussed in section 3. Section 3, we talked about mixtures and the various types of mixtures, and then we progressed into the different ways in which we can separate mixtures, okay? And those all really involve physical combinations, okay? Where things weren't any different than they were before they were mixed together, okay? They still kind of retained their properties. Today, we're going to be looking at really one of the core aspects of chemistry, and that is the elements themselves and the periodic table and compounds and the idea of making things chemically bonded together, okay? And so let's start off basic, starting off with elements. The elephant. We're not talking about elephants, are we? I'm trying to say elements and defined at the same time, and we get elephant. Anyway, elements are defined as a pure substance that cannot be separated into simpler substances by physical or chemical means. So it is as small as it can go. A single atom of an element possesses the properties of that element. There are 91 elements currently that occur naturally on Earth. The remaining 27 or so are synthesized or synthetically made by man or woman. Human, there we go. Each element has a unique symbol. I think it's missing some words there. That is universally accepted by scientists. And the symbol can consist of 2 variations. The first variation is the elemental symbol is a single letter. Bless you. Oh, I thought you were going to sneeze. Like carbon, nitrogen, oxygen, those all have single letter symbols, and it will always be capitalized. For elements that have 2 letters as their symbol, the first again will always be capitalized, the second will always be lowercase. You do not want to make them the same size, therefore it is not correct. Now, throughout the universe, at least the known universe, as much as we know at this point, naturally occurring elements are not shared equally, or not spread out equally, and are not as abundant equally. 75% of the overall mass in the universe that we know of is made up of hydrogen, the smallest, lightest element that we know. 75% of the mass of Earth's crust is composed of oxygen and silicon. Think about that. 3/4 of the entire Earth's crust made up of 2 elements. And out of our whole entire Earth's crust, is estimated that we only have 20 grams of the element known as francium. Francium is right here. It is a metal. It is highly reactive, and it is believed to be as reactive as actually, francium is considered to be radioactive. So,
Fun.
right? So, I mean, there's radioactive elements all throughout the Earth that occur naturally. So, I mean, it's nothing new, really. Which brings us to the periodic table. What this does, if you don't already know, is it organizes the elements into a grid of horizontal rows called periods and vertical columns called groups. I oftentimes call the vertical columns families, because about a handful or so of those vertical columns actually have names of the families. We've got the alkali metals, alkaline earth metals, the chalcogens, the halogens, and the noble gases. And elements, the reason why we tend to call them families as well is because elements in the same group, or vertical column, are going to have similar chemical and physical properties. Much like if you have siblings, there's a very good likelihood, again, not always, but a good likelihood that you will share some physical or other characteristics amongst you and your siblings. Much like the elements that are in the same vertical column are going to share very similar chemical and physical properties. As you go through the periodic table, you're going to start noticing that there is a periodic pattern as you move throughout, which gives us, leads us towards our name, the periodic table. And the current periodic table that we use was based off of really the initial, not the initial, I should say, a redeveloped, if you will, periodic table done by Dmitry Mendeleev. He was not the only one that was currently working on establishing a new organization system for the known elements. Lothar Meyer was also another scientist currently working at about the same time as Dmitry Mendeleev. But you don't hear anything about Lothar Meyer because Dmitry Mendeleev gets the credit for this because of his tenacity to get his table published. In fact, he kept getting turned down. He decided he was going to write his own textbook, and he included his table in that textbook and was therefore awarded with the publication of the first modern periodic table. Now, what he did was he decided to organize the elements that were known at the time into rows and columns based on their similar chemical properties as well as their masses. And Mendeleev, it wasn't, in terms of time period, it wasn't that long ago. And I believe it was in the mid-1800s when this was all done. At the time of Mendeleev's development of the periodic table, there were only just over 60 known elements when he did this. Currently, there's officially 118, I believe, elements that are certified and accepted in their place on the periodic table. And this is a 2013 version of the periodic table. You notice that I believe 6 of these boxes have a yellow highlight around them. At the time of this development or publication of this table, there those 6 that are highlighted had not been certified as official elements because they have to meet certain criteria. Up until the last couple of years, they finally have accepted, I believe, 3 out of those 6. So, yeah, that places us at about 118 or so, 115, give or take. Okay, but anyway, so we have doubled the number of elements that we know of since Mendeleev did this. But as he was developing it, he knew that there were some missing. And so he decided he went ahead and left spaces in the table to accommodate elements that just had not yet been discovered. And so he was able to go ahead and predict the properties of those elements that, again, had yet to be discovered, simply because of where they were located on his table. For example, he did not know at the time of his table development about germanium. Okay, germanium is right here. He called it, this unknown stuff, he basically left it blank, and he just gave it a name of Ica silicon. Ica meaning below. So below silicon, which is right there. And so based off of silicones and other elements that were known, their characteristics in that same group, Mendeleev went on to make assessments of what the properties of the unknown element should be. And when germanium was finally discovered and its properties tested and analyzed, we came to find out that Mendeleev's assessment of the unknown was nearly spot on to the actual proven properties of germanium. So,
powers to do that.
he might, but that's how well his table was developed. So that's basically what we use to this day. Now, if you take honors chemistry with me, we actually devoted an entire chapter to the periodic table itself, because there are far more bits of information and tools and trends that are just lying here in plain sight that we could use almost day in, day out. But all we see right now is a two-dimensional listing of boxes with numbers and letters in it. We know very little just by staring at it. But there is so much more than meets the eye, like transformers. Okay? To the periodic table. What's that? So again, this is even older version than the one hanging on my wall here. Doesn't have up to 114. Doesn't have up to 110 yet. So older one. So now that we've discussed single individual elements, we have to discuss compounds, because compounds are combinations of two or more different elements. And this is the key part, that are combined chemically. Compounds, however, are still classified as a pure substance. The reason why compounds are so important to understand is because most of the matter in the entire known universe exists as compounds. Water, table salt, table sugar, aspirin, they're all chemically combined elements to form these various substances. Now, over the entire expanse of scientific history, they have discovered about 10 million known compounds. Which again, you see the word or the number 10 million, like, wow, that's a big number, but I feel like it should be a lot more given the time of that science has been around. Well, the next line says we are still discovering new compounds at a rate of about 100,000 per year. 100,000 new compounds every single year, we keep adding to that 10 million. So then you start going, okay, yeah, that's a lot. That's quite a bit. So again, and these compounds are going to have their own unique properties and quote unquote abilities that are unique to them. Now, over the next probably 10 weeks or so that we have left, we're really going to be looking at chemical formulas. So we have to know how to do that and how to form them. But first, we have to know what they're made of. Chemical formulas use the element symbols from the periodic table so that we can identify the compounds. NaCl, sodium chloride, table salt. 1 part chlorine, 1 part sodium. We know that what the ratios are because of the subscripts or lack of subscripts that are on each symbol. H2O, composed of 2 parts of hydrogen to 1 part of oxygen. We know there's 2 parts of hydrogen because of the subscript of 2 on the hydrogen there. So, as I mentioned, compounds are going to have unique properties that are going to differ from their component elements. And compounds, since they are unique in regards to their components, they are produced from a chemical reaction. And it can go the opposite direction as well. Compounds can be broken down into simpler substances by chemical means. But in order to do so, in order to break it down, oftentimes that separation process is going to require energy, and that energy is typically going to come in the form of heat or electricity. And we just mentioned that the majority of the compounds, or I should say, the majority of the elements that we know of in the universe exist as compounds, which is a good thing. Because naturally occurring substances are typically more stable that way, being in a compound, than if they were just by themselves. For instance, a lot of the elements on the very left-hand side column of the periodic table, lithium, sodium, potassium, rubidium, cesium, francium, they're all metals. Okay, yes, sodium is a metal, but it's soft enough that you can cut it with a knife. However, you won't find the sodium in nature by itself, because when sodium is exposed to water, it becomes highly reactive. It actually bursts into flames and can explode if given enough peace. Which is why I use that and potassium and lithium in my classroom to demonstrate this fact. Okay? And so if sodium were just to be found naturally by itself, well, what is a component of air, especially in the really hot summertime around these neck of the woods?
Water.
Water, humidity, yes.
We go boom boom and
It would be a bad deal for sure if elements like sodium were just left by themselves. But as they combine chemically with other elements, they no longer are reactive. They become more stable. They calm down. Okay? Now, as we just got done talking about, that a compound, again, has unique properties that differ greatly, typically, from their components. Sodium chloride is a great example of this. So, obviously, sodium chloride is made up of sodium and chlorine atoms. Sodium itself, as we just mentioned, is highly reactive, fizzes, burns, can explode when added or exposed to water. Chlorine is a poisonous pale green gas. But yet, when you combine those two pretty dangerous individual elements, you get a white, unreactive solid that is used all over the world to flavor many different foods.
Fun.
All right, so we have an explosive element, a poisonous element coming together. It's like, oh my gosh, I just have to put this on food. Right? I particularly am not one that puts any extra salt on there.
Congratulations.
That?
Talking about chlorine, is that like something you also put in food?
Uh-huh. Yep.
You
It is.
ruined 90% of
It is.
things I enjoyed.
In fact, a lot of municipal water supplies utilize gaseous chlorine or elemental chlorine to help kill bacteria and other stuff in the water. Obviously, in pools, it's either in liquid or tablet form, but yeah, it's still chlorine. Which again may look like a big like mint, but you don't want to eat it, right? Yes. So now we're gonna get into a little bit of some mathing. Okay, not difficult math. Okay, but we're gonna start talking about what's known as the law of definite proportions. Okay, this is a scientific law stating that a compound is always composed of the same element in the same proportion by mass, no matter how large or small the sample. And I always like to use water. I can have an ounce of water, I can have a gallon of water. In both sample sizes, I will always have H2O. I will always have 2 hydrogens for every single oxygen, no matter what. And we relate these amounts of elements to one another, or to compounds, by what's called percent by mass. And what percent by mass is, it's the ratio of the mass of a single element to the total mass of the compound, and we express it as a percentage. So mathematically speaking, we take the mass of a specific element, divide it by the total mass of the compound, and multiply by 100. It's identical to determining a test grade. You take how many you got right, divide it by how many possible points you could have got, and multiply by 100. That gives you your percentage. That's what we're doing. We're just trying to figure out how much of a, really if you think about the total mass of a substance as a pie, again, we talked about graphs and everything like that a couple weeks ago. Think about the entire mass of a substance as a pie. You want to see just how big of a slice of that pie each element makes up. So first, you have to determine the mass of the individual element. Oftentimes they're given to you, sometimes they're not. You got to do a little algebraic rearrangement. Then determine the mass of the entire compound. If you don't know both of those, you cannot solve this problem. Okay? Once you've determined those, you're going to plug them into this formula, and it's solved mathematically. Let's do a couple different examples here. You have a 78.0, sorry, I lost my whiteboard. 78.0 gram sample of an unknown compound, contains 12.4 grams of hydrogen. What is the percent by mass of hydrogen in the compound? Okay. So 78 and 12.4. All right. So, so we got 12.4 grams of hydrogen, and we had 78.0 grams of total substance, right? Okay. And so what we just have to simply do is take the 12.4 grams of hydrogen divided by the overall mass of the substance, 78.0, and then multiply by 100. I want you to solve that. And I'm going to have you give me an answer here in a moment. 15.9. And don't forget your label, excuse me, of percent. But what happens if we're not given information that is necessarily 100% straightforward? For instance, our next problem. Okay, move away, there we go. If 1.0 gram of hydrogen reacts completely with 19 grams of fluorine, what is the percent by mass of hydrogen in the compound that is formed? Okay, so we have what, 1.0 grams of hydrogen and 19.0 grams of fluorine. So these two substances react with each other. Based off of hopefully our knowledge of the law of conservation of mass, when these two reactants combine or react together, how much should my total mass of my new product be? 20. Because the law of conservation of mass states you cannot create nor destroy mass. All mass must be accounted for from beginning to end. Okay? So this means that we should have 20 grams of hydrofluoric acid. And so we are asked about what is the percent by mass of hydrogen. So we're going to take the 1.0 gram of hydrogen divided by the 20.0 grams hydrofluoric acid, multiply by 100. And what do you get? What's that? 5.0%. We got one more slide to do, and then I've got a question that I want to go, another math question I want to go over. So our last slide deals with the law of multiple proportions. So the law of multiple proportions states that when different compounds are formed by a combination of the same elements, different masses of one element combine with the same relative mass of the other element in whole number ratios. And so our examples here are H2O2 and H2O. And both of those examples of substances contain hydrogen and oxygen. Water, being H2O, has 2 parts hydrogen, bless you, to 1 part, bless you, 1 part oxygen. The other substance, which is hydrogen peroxide, H2O2, has 2 parts hydrogen to 2 parts oxygen. Now, hydrogen peroxide contains twice as much oxygen compared to water. So the mass of oxygen in hydrogen peroxide to the mass of oxygen in water would be considered a ratio of 2 to 1. That's where the whole idea of multiple proportions comes from. And it also shows you just how crazy chemistry is. H2O, a substance necessary to sustain life. H2O2, you ingest it, you cease life. Water is necessary. Hydrogen peroxide is essentially poisonous. So just by the addition of a single oxygen atom, which again, oxygen too is a essential part of life. Now, before we wrap things up, I have a problem. Well, I don't have a problem. I have a question. Well, some say I might have a problem. And that question is this. Oops, let me zoom out here. Sucrose is 51.50% oxygen. Okay? How? Oop, I can't even spell how. People want to spell home. how many grams of oxygen are in 20.0 grams of sucrose. Now I want to show you this question. Okay, so it's a little different than the two that we just did. And sucrose is 51.5% oxygen. How many grams of oxygen are in 20.0 grams of sucrose? So here's the thing. We have to think about it in terms of that formula that we just saw. Okay, where percent by mass is equal to grams of element divided by grams of substance multiplied by 100. Okay, and that gives us our percent. So if we already know our percent is 51.50, okay, and we set it up kind of going backwards, meaning we have times 100, we could treat this like an algebra problem, okay, where we are trying to identify how much or how many grams of our oxygen is present in this overall substance that is 20 grams if it makes up 51.5%. And so X becomes our oxygen divided by our total mass of our substance. And then we just work backwards to solve for X. So the first thing I'm going to do is I am going to divide by 100, okay? And so I'm going to get X equal to 20.0 grams is equal to 51.50% divided by 100. You get 0.5150. And so I'm not quite done yet because I still have to solve for X. So in order to solve for X, I'm going to multiply both sides by 20. And so I now get X is equal to 0.5150 times 20. I get 10.3 grams of oxygen. So again, I just treated it like an algebra problem. But instead of setting it equal to an unknown percentage, I knew my percentage. I didn't know my mass of my specific element. So I just switched around my variables, my unknown, and solved for it. Okay? So I just wanted to bring that one up to show you that there are multiple ways that these questions can be asked. Okay? So I'm going to, yes. Yes, I'm going to show the last slide, and as I'm doing so, I'm going to end this recording. Those of you at home, thank you for watching, and make sure again for the 3.4 homework, you get it turned in and submitted before the end of the evening on Sunday.